One of the keys to looking at a problem like this is getting through all of the verbiage at the beginning. Don't get bogged down with the verbiage at the beginning. If you do, start somewhere and just write down all the givens and be done with it. But when you have all that verbiage at the beginning, it confuses a lot of people. Why do you do it then, Coach? Well, I do it because that's the way real life problems turn out. So this 10 right here is N. There's my X bar. There's the sample size. Here's HO and HA. Here's the significance level. And question 1 says calculate the probability of a type 1 error. So the type 1 error is simply alpha, which we do in orange. So alpha for this problem is 0.05. Be careful. A few of you guys get confused on this, and sometimes you look at that, but you write 0.5. So just be cautious of that. So the alpha level is 0.05. Number 2 says write the rejection region in terms of Z. Is this a one-sided test or a two-sided test? Two-sided test. So if the orange region is 0.05, I've got to divide that by 2. I get 0.025. And either look up 0.025 on your chart, do it on your calculator, or use your brain, and remember that it's 1.96. So the rejection region means that I'll reject HO out here. So I'm going to reject HO if my Z is greater than or equal to 1.96 or Z is less than or equal to negative 1.96. Some of you guys might like to write it like this. Reject HO if the absolute value of Z is greater than or equal to 1.96. I don't really care for absolute values very much. I always get them confused, but that means the same thing as this. So you can write it either way. Now it says unstandardize the fences and write the rejection region in terms of X, or in terms of crop yield. So I'm going to unstandardize these dudes. That means 1.96 equals wherever the fence is minus the mean divided by sigma over the square root of n, which is 0.83 divided by the square root of 10. And then I unstandardize this fence as well. Negative 1.96 equals X bar minus 0. And it's 0 because the HO is mu is 0. That's where that came from. When you solve these two things, you get 0.5144 and negative 0.5144. So I'll reject HO if the X bar you get is greater than or equal to 0.5144 or X bar is less than or equal to negative 0.5144. So then on number 4, it says the researchers who carried out the field trials suspect their results might be affected by low power. We want to be able to detect a difference like 0.5. So that's the new true blue mu. And this alpha level that they gave me, thankfully, it's the same one they're talking about before, so I don't have to change anything. So now I'm going to draw the picture, and this is where I get two normal curves on the same graph. So I'm going to draw these pictures out here, and I've got my original curve where the center was 0. I've got my fences drawn in here and here, and in terms of X, I just figured out this is negative 5144, and this is positive 5144. You might have written these values on here as well, negative 1.96 and 1.96. I think a very important part is to actually write fail to reject in here and reject on these other parts. And I think that's important because when you draw another curve on here, the whole thing gets a little more convoluted and you get confused about what's going on where. There's my alpha region, that's the orange part. And now I draw the new true blue mu at a center of 0.5. So that's a little confusing here, but it's going to look something like this. I know 0.5 is really close to 0.5144, but you don't have to draw it really, really close. Just draw it to the left. Okay, so you can see what's going on. This problem asked me to find the probability of type 2 error. What is that called? Beta. So beta is this area in here. Beta is a type 2 error, or it's the probability of a type 2 error, and it's when I fail to reject HO, but I ought to. So I fail to reject between the fences, so I shade between the fences, but I'm living under the blue curve. You're welcome to bring map colors or crayons or markers to your test if you think that different colors helps you. So I get that, and now I need to standardize it. Negative 0.5144 minus the mean, the new mean, over sigma divided by the square root of n, less than or equal to z, less than or equal to 0.5144 minus 0.5 over sigma divided by the square root of n. Now I want everybody to try this. So for simplicity's sake, girls standardize the one on the left, guys standardize the one on the right. So everybody gets some practice. So this gives me the probability of negative 3.86 is less than or equal to z is less than or equal to 0.055. And so now I can look this up on my chart, or I can use my calculator, and I get I believe it's 0.52. So in this case, we get the probability of a type 2 error is 0.52. What that means is there's a 52% chance that if the truth is 0.5, but I thought the truth was 0, I'll get an X bar that tells me to fail to reject 0. I'm going to say that one more time. If the truth is 0.5, but I think it's 0, when I take this sample size of whatever size it was, 10, there's a 52% chance that my sample size will fall in the region that tells me to fail to reject, to keep believing 0. Mistakenly, because 0 isn't true, 0.5 is true. That's what a type 2 error is. Now question 5 turns that on its head and says, what's the power then? Well, power, of course, is 1 minus beta. I guess I could write it like that. That's 1 minus beta, which is 0.48. In other words, there's a 48% chance, if I believe 0, but 0.5 is actually true, there's a 48% chance that my X bar will fall in the reject region of the blue curve, thereby telling me to reject HO, thereby making a correct decision. That's power. That's a good thing. How can I improve the power? A couple of different ways. Okay, so one way to make power bigger is to make beta smaller, and I make beta smaller by making alpha bigger. So I can increase the probability of a type 1 error. That would decrease the probability of a type 2 error, thereby increasing the power. So if I changed my alpha level, that would help power. Okay, how else can I help the power? Increase the sample size. If I increase the sample size, then both of my graphs get taller and skinnier. Last period, somebody said they get smaller. They don't get smaller. They get narrower because the area under them is always 1. So if I take a bigger sample size, both my pink curve and my blue curve get taller and skinnier, meaning I'm less likely to make errors, less likely to get stuff outside the rejection region. So that's a great way to do it. If I gave you a different version or another question that said, what about the power at 0.6? Would the power at 0.6 be more or less than the power at 0.5? Well, think about this. What would beta be like if I moved the blue curve right a little bit? Beta is going to be smaller, exactly. So what's going to happen to the power? It's going to increase. Now, looking at the graph, maybe you can figure that out, but let me help you also just with the concept. If I think the truth is here at 0, but it's actually at 0.5, that's a little harder to tell than if the truth was actually at 0.6. If I thought that the women on the island were 64.5 inches tall, but it turned out that they were 64 inches tall, that's pretty hard for me to pick up on. On the other hand, if it turned out that they were 24 inches tall, that'd be real easy to pick up on. The power would be a lot bigger. If the true value and my belief are a long way apart, it's easier for me to pick up on that. That picking up on that is called power. If I thought you were a good person, but you're really a low-level slime, how hard will it be for me to pick up on that? Not very hard. The trick is if I think you're a good person and you're a really sneaky person. So it's hard to discern that difference. The power is a lot tougher right there. That's the power question and the kind of stuff you need to be able to go through on your test.